Greetings everyone, I am Oshita. So today I will be speaking about temporal data mining for time series forecasting. In this presentation, my agenda is to talk about its introduction, why I choose this topic, key formulas, numerical example, application, challenges, future research and conclusion. Now, what is temporal data mining? Temporal data mining is the non-trivial extraction of implicit, potentially useful and previously unrecorded information with an implicit or explicit temporal content from large quantities of data. This is an extraction. This is a definition I extracted from an article called temporal data mining. Now we will discuss what is temporal data mining for time series forecasting. It is the process of extracting useful patterns and knowledge from time dependent data. Unlike traditional data mining, it takes into account the sequence and timing of events. It is a powerful approach used in everything from stock predictions to weather forecasting. Now, we will discuss types of temporal data. Uh, to discuss this aspect is very important because understanding the nature of time-based data helps us choose the right analysis methods and models for forecasting and pattern detection. Now, what is time point data? Each observation is tied to a specific point in time. Example, timestamp associated with a particular temperature. Time interval data. This is where each observation is tied to a range. It is used for measuring data over durations like hourly, daily, or weekly use. Suppose for an energy consumption 1.2 kilowatts, the time interval is 8 to 9. Now, what is time series data? It consists of observations recorded sequentially over time. An example is daily temperature readings collected by weather station. Illustrate time series data used for climate analysis and prediction models. Next is cyclic data. Data that repeats in cycles, example daily, seasonally, and yearly. This captures cyclic behavior such as weekly patterns in store sales. Now, why I choose this topic? uh, there is an very much importance for temporal data because time dependent data is everywhere in stock markets, weather, healthcare, and business analytics. When we understand patterns and do time series forecasting, it helps make informed decisions. Need for accurate forecasting. Organizations rely on forecasting for demand planning, financial analysis, and risk assessment because forecasting aids decision making and planning. Temporal data mining techniques like ARIMA improve prediction accuracy. In business, it helps companies predict sales and demand. In healthcare, it assists in predicting disease outbreaks. It is not that it will predict it is not that it will predict correct predictions in healthcare, but these predictions may help them uh, improve themselves, improve the domain. Moreover, with the rise of AI and big data, temporal data mining is gaining importance as organizations seek data driven strategies. Additionally, I found this a topic interesting because of its mathematical depth and real world applications and real world applicability. Methods like ARIMA, LSTMs, and Profit provide powerful techniques for accurate predictions. Now, there are several techniques for time series forecasting. There are statistical approaches, ARIMA, SARIMA, and machine learning approaches, XGBoost, hybrid approaches, Facebook Profit, and deep learning approaches such as recurrent neural networks, long short-term memory, and transformer models, PFT time GPT. Now, these are the key formulas I used in my PPT. I will I will limit I will limit my numerical explanation up to moving average smoothing and ARIMA 100. Where these are the formulas I used in my presentation, which is moving average smoothing is yt minus 1 plus yt minus 2 plus yt minus n is the number of observations we choose and divided by n. Mean is the sum of observations by number of observations. AR coefficient is calculated using LSE where yt is the current value, mu is the mean, and yt minus 1 is the previous value. ARIMA equation is as follows. Now this is my data set. Here I choose a small data set for getting an accurate calculations, but basically time series data will be larger in size. Here I applied moving average smoothing to highlight the overall trend. Though not sophisticated, not sophisticated as ARIMA or LSTMs, it will provide a quick baseline for forecast. This information helps businesses optimize stock levels and marketing strategies. First, the process to apply moving average smoothing is choose the window size. When we choose the window size 3, we will apply average for the past 3 days and then apply this formula. Now compute moving averages for each time point. Start from day n plus 1 because the first tenders don't have enough past data. The mean and past n values for each time step. When we calculate for Wednesday, it comes as 150 because 148 plus 152 plus 150 gives 150. Likewise for Friday, 148 plus 151 plus 149 by 3 is 149.3. Even for Saturday also the value is same. Here from 151 the value is dropping to 149 when it comes from Thursday to Friday. Since it decreases slightly, it shows a downward trend in sales. If sales were increasing, it would also rise. Moving average smooths data but does not predict future values based on past dependencies. To get an accurate predictions, we need ARIMA because it captures temporal relationships and temporal dependencies. In our data set, In our dataset, it shows dependencies between past and current values. Today's cells are clearly influenced by yesterday's. That's called autocorrelation. Therefore, ARIMA 100 captures this relationship. Since our data is stationary, we don't need differencing. So ARIMA 100 can be used. Now, what is ARIMA? ARIMA is a fundamental time series forecasting technique which consists of three components P, D, and Q. P is set to 1 because sales depend on previous day. One value. Since our data is stationary, we don't need difference thing. We set D is equals to 0. Moving average terms are used to correct random shocks in data. Since the data doesn't show strong random fluctuations, moving average isn't needed. So we set Q is equals to 0. Now these are the steps to calculate the ARIMA. First, we calculate the mean of the data, which is we sum up all we sum up the values of sales and divide them by 5, which is the number of observations. We get the value as 150. And next we calculate the AR coefficient by using this formula, which is the AR coefficient using least squared estimation. Yt is the current value, mu is the mean, and yt minus 1 is the previous value, minus mu is the mean divided by summation of, again, yt minus 1 is the previous value minus mu of whole square. When we apply summation to both of this, we get the LSE, that is AR coefficient, which is minus 0.778. Since there is no moving average component, we need not calculate it. But for other models where there is a moving average component, we need to calculate it. We predict sales for day 6 using the AR1 equation. The equation is a bit different than the previous one I showed here, because here there must be an error term also, since future is unknown to us, it is expected to be 0 and we drop the error term here. But here our mean is 150, and in software the equation is C plus mu plus phi. Mu is the mean and phi is the AR coefficient. Yt minus 1 is the previous value. So C is represented as mu 1 minus phi 1 here, which can be retermed as this equation. Yt is equals to mu plus phi 1, yt minus 1 minus mu. Minus is not clearly visible there, but minus is there. Yt minus 1 minus mu, which gives the value as 150.78. Concluding ARIMA as, when we substitute these values in this particular equation, we can use this equation or this equation. When we substitute these values, both gives the same value as 150.78. Concluding that ARIMA is more accurate because it learns patterns from past data, making it more reliable. Now, applications. When we analyze historical stock market trends and detect seasonal patterns, it helps to predict future stock prices more accurately. Temporal data mining uncovers these hidden dependencies, and when we apply correct time series forecasting model, and when we detect these models, uh, temporal data mining helps to improve investment strategies. Retail. Discovering purchasing trends and seasonal fluctuations. Seasonal fluctuations are discovered by Sarima. In sales data for demand forecasting, temporal pattern recognition improves inventory optimization by identifying recurring behaviors. Time series forecasting models are used to predict future sales and manage inventory. In weather forecasting, when we mine historical climate data to uncover these long-term trends and anomalies in temperature and rainfall patterns, advanced techniques like LSTM capture nonlinear temporal dependencies and improve accuracy in climate trend analysis. In energy sector, when we monitor electricity consumption patterns over time to optimize power grid efficiency, temporal mining techniques help to detect sudden demand shifts. When we detect these sudden demand shifts and we select a proper time series forecasting model, it will predict more accurate value. Challenges: data quality issues. Sometimes time series data consists of missing values and outliers or noise, which may be problem. Pre-processing techniques or smoothing techniques must be applied to clean the data. Here I applied smoothing technique to highlight the trend, but normally smoothing techniques are applied to clean the data. Handling non-stationality. Many time series data exhibit changing trends or seasonality over time. Advanced techniques should be applied to handle such complexities. Multivariate and external influences. Many real-world forecasting techniques depend on multiple factors such as stock prices are affected by news or interest rates. Incorporating external variables into time series models adds complexity. Concept drift. Patterns in temporal data change over time due to external factors. Example, economic shifts and policy changes. Forecasting models must be frequently updated to adapt to new trends. High computational complexity. When we scale large temporal data sets, it requires significant computational resources. Real-time forecasting applications demand efficient algorithms for quick analysis and decision making. Choosing the right model and parameters. It is not guaranteed that we choose ARIMA for a particular data. Depending upon the dataset, we have to choose the better forecasting technique. But selecting optimal values for ARIMA, PDQ, or deep learning hyperparameters is also challenging. Now, future research. Hybrid models combining ARIMA with deep learning, because ARIMA will capture simple trends and seasonal patterns will be detected by SARIMA, but deep learning patterns is used to detect trends in complex data sets. Therefore, when we combine this both, it is used to capture both simple and complex patterns in time series data. Anomaly detection: when we enhance models to quickly identify unusual changes in data, such as fraud in finance or sudden demand spikes in retail, it may help more in time series forecasting. Big data forecasting: developing powerful algorithms that handle large-scale time series data from IoT, stock markets, and climate studies will help to forecast more accurate and better values. Example: explainable AI in forecasting, making AI models more transparent so that users can understand why a prediction was made, improving trust in automated forecasting. Conclusion: temporal data mining and time series forecasting play a crucial role in uncovering patterns from historical data to make accurate predictions. The ARIMA model is fundamental technique, but based on data, we should choose which forecasting technique to apply. With advancement in AI and hybrid models, the field is evolving rapidly. We have seen how moving average is applied. We have seen how moving average helps in basic smoothing, and but ARIMA gives better results when past values influence the future. With the rise of big data and AI, the field is set to transform the industries by enabling smarter data-driven decisions. As research progresses, temporal data mining combined with advanced forecasting models will continue to transform industries like finance, healthcare, retail, and energy, making data-driven decision making more powerful than ever. Thank you.